Good afternoon. On behalf of the ASTN, I'd like to begin by acknowledging the traditional owners of the land on which we meet today. I would like also to pay my respects to elders past, present, and emerging. Welcome, everyone. Today's event is part of Australia's AI Month, where we showcase capabilities, talent, and potential. As an industry-led, not-for-profit membership organization, we connect sports tech in Australia to global markets to help build the capacity and capability of the sector. This event today is made possible by the Western Australian Department of Jobs, Tourism, Science and Innovation, the Queensland Investment Corporation and their Venture Capital Development Fund, and the Victorian Department of Jobs, Skills, Industry and Regions. My name is Martin Schlegel and I'm the chair of the Australian Sports Technologies Network, ASTN. At ASTN, we have showcased AI capability in previous sessions. From high performance and elite sports, as well as the business of sport, we've shown a highlight or light on the capability and the possibilities that AI provide to sports. And today, we're extending this showcase across the globe. So it's my absolute pleasure to welcome Mark Xu of TNG Technology Consulting. Mark comes from a Paralympic background and joins us this afternoon from Cologne in Germany. So good morning, Mark. It's a very early morning over where you are, and welcome, and we're delighted to have you.
Yeah, Martin, thank you very much for the introduction. It's a pleasure to be here. Yeah, and a very early good morning from Cologne. It's roughly 5:30 at the moment, so that was an earlier wake up than usual for an IT law. Let me start with the presentation and give you a few words. So you should now be able to see my presentation. Yeah, that looks good. Yeah, today I'm going to talk, as already in the announcement, from athletes to algorithm. So talking about an AI Canoe showcase and yeah, telling you the story on how we improved that with AI. A bit about me. My name is Mark Xu. As already mentioned, I have a background in Paralympics. I was a 400-meter wheelchair sprinter, participated at 3 Paralympic Games. And beside that, I studied physics, did a PhD in there. My sports career ended in 2017. My academia career ended in 2019. And then I moved over to TNG Technology Consulting. We are a Munich-based company, but going around the globe. We also now have an office in Melbourne, which is now also expanding to New Zealand. We are roughly 900 people at the moment and tackling all kind of interesting IT challenges as a consultancy. But that's not only our core business, or that's our core business, but we also have the very famous innovation hacking. If you would like, you can follow the QR code or the URL at the very bottom, which the innovation hacking is a small department. I would call it in a summary, research and development, where a few enthusiasts tackle the newest technology on some problems that haven't been solved before. So what you can see here in the small video clip is some virtual reality stuff and people sitting there in one of our offices and hacking stuff to see if they can make use of the latest technology. So here you see a VR game. They're also famous for live deep fakes. Here that's a game show that was deep faked afterwards. You can see everybody is Jonas Meyer. And that also goes to AIslides.com. You can visit that website. There you get a short presentation from a prompt, which you just can type in. And then after a few seconds to minutes, you get a small slide deck, which you can use. This presentation has been made without these AI slides. And so what are you going to expect today? you get a first brief introduction into the problem. Then what I really would like to show you is how we tackled it down, because nowadays AI is, of course, a huge hype. When we started the project a few years ago, it wasn't that much, and still you can't just type in also not today into GPT, give me an analysis for Canoe athletes, and then it gives you the code and you're good. You still need to understand the business case, how it works, how you can track down the individual steps, how you can reproduce how a human works, and this then transfer to the code. This will be given here. We will also give you an introduction and an overview of the challenges, because not everything worked out the first time, and then in the end tell you how good it worked and how we can continue. So the challenge. I mean, as I already mentioned, I have a background in Paralympic sport. I studied in Heidelberg, which is between Frankfurt and Stuttgart, and I have a close connection to the Olympiastützpunkt, which is a performance center where the athletes can train and prepare for the games, Olympics and Paralympics. And when I then switched to TNG and met the innovation hacking, we also went back to the Olympiastützpunkt, or actually I did, because of an event where we all gathered and had a talk to one of the heads and said, hey, I work there at a really cool company. Maybe we can cooperate at some level. And after some discussion, we thought, okay, that's not what it works. But in the end, he came up with, I have here this problem. When there's a lot of canoe sports going on at that place, he says, when I want to improve the technique of a canoe athlete, at the moment, what we do is we have the athlete paddling on the water. And besides that, next to it, there is a boat with biomechanics on it, who has a camera and films it. And afterwards, we take that video file and go through it frame by frame, because from the textbook, we are interested in these 4 paddle poses. I think you can't see my mouse cursor, but I just point to the top left image, where you can say, okay, we are interested in the angles of the paddle with respect to the water line, when the paddle first hits the water, when it's fully submerged, when it is still submerged, and when it starts to rise above the waterline. And when we do that, well, that's a very, very tedious task, because you have to go through frame by frame and mark that. Do we have a chance to automate that it's not a process which takes a studied biomechanical engineer 20 minutes per athlete per video? We thought, maybe. And that's what the challenge is. So I will explain you a little bit about the frame selection. So how do we actually get the right frame when the paddle is changing the state from one of those poses I've mentioned before? How do we align the canoe and get an idea, okay, where is the canoe? And then in the end, doing the annotation, getting the angle of the paddle toward the waterline. So first of all, I would like to start with a bit of an overview. So we are going to teach the computer how to view, to understand an image. This is summarized with computer vision. Computer vision is actually quite a lot of combination of various tasks and fields across IT and physics and mathematics. But in the end, if you track that down in everyday life, well, what you have here is a snapshot filter, some object detection. That's what computer vision is then applied in real life. And behind that, we have neural networks. So what is actually a neural network? Let me just briefly introduce that with what is a neuron. A neuron is something where you have an input and you have a threshold. If the threshold isn't overcome, then the neuron doesn't fire. If it overcomes, then it fires. So, and this is a behavior you can mathematically construct again in a computer. That's the reason why they're called neural networks, because the way our neuron works, we then emulate in a computer with a reload function. So what you have here in is various inputs on the very left side. those are combined, and only if you're above a certain threshold, then you have the activation and it fires. You have your strong nonlinear behavior. And now let's go to a very famous neural net, which is mobile net, which is for object detection. And how does that work? Well, you have here on the input, you have your video with 224 times 224 pixels times 3 colors. So that's a very rough picture at the moment, not a high resolution, but that doesn't matter. It's good enough for our case. And then you send that through various layers that will become important in the end. And it maps it down to 128 objects. So a mobile net is able to detect 128 objects. And what does it do and how does it help you? Well, you give in, for example, here this duck, you send it through the neural net, and in the end, you have the classification of, hey, that's a neural net, that's a duck. And now let's try it out briefly. So here you can see my home office without the virtual background, and if I now place here the famous coffee mug from Heidelberg, then it helps me and says, yep, that's a coffee mug. I can clearly see that. And if we now go on with deep learning, so now we have a neural net, and just let's briefly jump into how we can train such a neural net. That's called deep learning. As mentioned before, we have these input parameters, and we have a weight and a bias, so we can weight them and say this is more important than others, then we want to focus on those parts. And if we can also add biases, so that are the knobs to turn on that neural net when we want to retrain it. And by that, we can actually move it toward the region that we want. That will become important later on. And you do not only have one knob, but as probably a few have already noticed, when they're coming up new models from ChatGPT, from Facebook, there are billions of parameters. So it's really a big drawer with many knobs that you have to turn. And luckily, here we can make use of mathematics with a gradient descent, where you say, okay, you wiggle at all these knobs and you make a loss function. So you give him the training data, you say that's a duck, and in the end, you want to have the neural network to recognize it as a duck. Then you give in an image with a coffee mug, which is labeled as a coffee mug, and in the end, you want to have the neural net to be there to rate it as a coffee mug, and you have a feedback loop. Every time the neural net is right, you give them feedback, yes, it's right. And if it's wrong, then you give kind of a punishment, which is a loss function, and you try to minimize that loss function with that neural net. That so in the end, it has the best possible result on your trainings data on how to get, okay, the recognizing objects with this deep learning technology, and here the gradient descent as a mathematical technology behind it. Okay, so that so far for the short background in AI and deep learning here. And now let's move on to the first problem of our threes, that is the finding the waterline. I mean, when we want to get here and say, okay, we want to have the Canoe in the image, we want to have it always on a horizontal line. That's the first part. So just here, tilting it a bit that the Canoe is horizontally, because that makes things easier in the end. And then we want to have here the waterline. And how do we get that? That's the first part, because also, I mean, if you draw as a biomechanics, if you draw in the line, you also recognize the waterline and the paddle. So the first step is the waterline as a base image. And what the human does is that it recognizes and says, okay, I do see a foreground and a background. And that's what we do. We do a segmentation. What is foreground? What is background? And also there helps us, again, a computer vision technology. And just let's briefly jump into it. Now I have transformed into a little Yoda here now, having clearly the foreground background separation. Also here, the coffee mug I can put in the foreground, but when I place it here, it's still connected, but there it starts to get out of the foreground toward the background. Okay, with that technology, that worked. So what's next? We have found here the foreground with the canoe. We do not care about the upper part of the athlete here, so that's why it's cut. And to see in which direction the canoe is moving, which is also important for our analysis, we use the kind of feature tracking. Here, of course, the human would have the knowledge directly, but also with feature tracking, that's a kind of easy approach as you say, yeah, we see, for example, some stickers, here some knobs, and parts of the boat which clearly stand out. We track them, and with that, we can have a principal component analysis and seeing that the canoe is moving to the right. Okay, with that, we have solved our first problem. We have the foreground-background separation, we have the feature tracking, we have the principal component analysis, and with that, we have our canoe stabilized, and we have found the waterline. That's part 1. 3 to come. Next part is the annotation. I mean, also when we draw images, or if we draw the angles in, we say, okay, we have the waterline, we have here the paddle, we can clearly see the paddle, and then make use of that and say that's a waterline. So that is our target for this section. Just need to drink briefly something, just how do we find a paddle in a canoe image? Well, the straightforward approach would be to directly tell the computer find the canoe paddle. This is a bit difficult because there are not that much data available of neural analysis networks that find paddles per se. So what we do is, usually the canoe paddle is a very, very straight line, which is connected to the hand of the athlete. So by finding the hands, we usually have a proper idea of where to find the canoe paddle. And now let's briefly jump into OpenPose. What we do here, we use OpenPose, which is now not running really smooth here on my laptop, which says, okay, it is trained for the human body to detect several parts like wrists, eyes, shoulders. And with the wrists, we come already at that part where we say, hey, that's not that bad. We can use that. So what you do here is you bring the neural net, you bring the image in, you send it through through OpenPose, through your neural net, which is specialized now on human parts, and then it says, well, hey, you have here the right eye, the left eye, the wrists, the arms, and with that part, we come closer to get the computer an understanding of how a human looks like and where the paddle could be. Actually, we use here heat maps, which is a part which I will briefly jump over. But in the end, we now have the next step that we have here the human rowing, paddling on the boat, on the water in the canoe, now following OpenPose and saying, hey, we have here the eyes, the shoulders, the hips, the knees, and the wrists. And the wrists will become the most important part because with the wrists, we have a proper idea on where the hands are, because we know if we go from left to right, we know where the elbow is, and usually if you have an idea from the distance from the elbow to the wrist, you also have an idea where the hand is, which we make use of, because we give here this bounding box, which is in white, which was in green, which was in blue before, and now we go for a finger tracking, because if we tell our computer, that's also something we learn, do not feed in the whole image. The neural nets and the computer vision technologies are usually very specialized for smaller parts and do not or cannot handle if the information is very shallow in the image. It has to be the major part in the image, then the analysis works well. Otherwise, it doesn't. So always help the computer narrow down the focus in the image to give an idea, okay, where to find it. And now we have an idea where the fingers are, which helps because we could track it down to where the hands are. By that, we can narrow it to give the center of the center. And hey, here now we can follow the paddle quite well. And now what we need to do is finding the center of that one, drawing a line through it, and then we have our annotation. So again, what did we do now? We tackled the second challenge of our 3 challenges. We have here now OpenPose running on the video, telling us where the wrist. From that, via finger tracking, we find the hands, we narrow it down, and then have an idea where the pedal is. And in the end, we are here, and hey, that looks already like an annotated image. So the first 2 of the 3 problems are solved. Just to give a quick reminder, we now want to find the pedal poses, because that's where we have literature values which says, hey, you have a dedicated angle. When you touch the water, it should be 70 degrees. When you come above the water, it should be 130 degrees. So that's where we want to compare the image or the video to the actual analysis of the athlete on the water. So the next part is how to find the right image in that video. Jumping briefly in, that's what we want to find. We want to have here touching the water 40 degrees, submerged 70 degrees, coming above the water 130 degrees, 150 degrees when we are completely above. And how can we tackle that down? Well, what you can say, you always have a stage transition of a paddle that is completely above and below. And these 4 paddle poses are then just a transition of these 3 from being above, half submerged, and then fully submerged. And what I told you, what we did so far is you have an image, which you put into a neural net, and then you have a classification in the end where you say, okay, we have here paddle state 1, 2, 3, 4. For that, what we do, that's also, again, the same lesson applied as before, narrow down the region of the paddle of the image you want to analysis. So here it's narrowing down to the paddle blade. What we do here is we have an idea where the waterline is, we have an idea where the paddle is, we have an idea if we're going right or left. So we know which end of the paddle the computer has looked to, and then we say, hey, dear computer, only this blue box we will give you. We will send that to a neural net, and then in the end, having the data analysis. So model, data, and we're good to go. Yes, that would be the happy case. Unfortunately, there are not that many publicly available data on Canoe analysis and paddle detection in which state they are. So that didn't work out. What we did is we trained the neural net around. That's the reason why I told you at the very beginning how to do that, because, well, you have to label data and feed that into your neural net, and then train with that neural net that in the end, with the labeled data, it is able to classify which paddle state the paddle image it gets the paddle state is in. And what we do here, we first go through videos, many videos, and get these blue bounding box part image and get that extracted. That's the first part. That's the easy part. That's how it looks like in the end. So we have narrowed it down. If you look at it for too long, you get a bit dizzy. So I won't stick here for too long. For how to do that with many images, we went for 35,000 labeled frames. Luckily, we had a working student where I'm very grateful still today that he managed to label all these images. We gave him a bit of a hand. So here, tooling is the key. We had these images, and all that needed to be done is by pressing an arrow on the keyboard, that it's not that you have to write up, down, left, right, but here really minimal input. That's up, that's down, that's in between. And with that, we were able to label these 35,000 frames, put it into the machine learning that I presented at the very beginning, and do kind of a transfer learning. Because remember from before, we had here, that's a layer of the mobile net, and we had here 1,280 objects that were recognizable by the new mobile net. And now we narrow that down to 3, because we only need to have these 3 outcomes here. And that's what we did. And with that, we now have a pedal state change detector where we say, hi, that's cool. That seems to work out quite nicely. You can see here now the video is going through. At the moment, it's fully above the water. You get a good short flash at the top. When it changes, there was a pedal stage, true. Now it's penetrating the water, now it's underwater, now it's penetrating, and now it's above the water. And that's how now we have the analysis. So, hey, that looks really promising. With that, we get here now the analysis of our 4 paddle states. And with that, one could think we are done. So just let me get it briefly summarized. So we have here the foreground-background separation, the feature tracking. With that, we get an idea in which direction the canoe is moving and where the waterline is. Then we have the post-detection. We go through the hands, find the hands, find the fingers, connect it, have the line. With that, we have the paddle line. With that, we get the annotation of where to find the angle or how big the angle is. And with narrated down to the paddle itself and sending it through a classifier, we then get in the end the classification of our 4 paddle poses. One could think we're done with that because it's so easy. We missed one step, which took us quite a while, because how good did we do actually at the beginning? Well, the finger tracking and stuff like that, it didn't work out that well if you just take one picture into account. We had these kind of failures, kind of often. We had only a success rate of detecting the correct paddle state change in a range of 37%. We had incorrect annotations. The waterline here was off. So it was a mess. The paddle was not detected. This was not that uncommon here. And how did we change that? How did we fix that? One important part was moving from OpenPose to YOLOv 3. And the more important part is having the temporal component also in the Canoe analysis, because the human has a temporal perception and the computer hadn't so far. We only got them one image after another with no idea how they could be connected. I mean, we know if the hands are here, they cannot jump through time and space and be at another point in space-time without having a smooth transition. At least that's what we hope for. And that's what we implemented here by having a feature tracking, having a tracking of the center of the hand and fitting that. That what you see here with the blue dots. That is where the hands were before. And in the brownish line, that's the fitted path of that one. With that, we can detect outliers and also reject outliers to say, okay, that doesn't work. Then we added some line finding in our image. So also what the human eye does is very good at finding lines in images, and also can neural net do that. And with that, we are able, okay, to track down, hey, here the paddle is really just here at that angle, because we find a straight line, which is not that common in images otherwise. And to have a look at it, what you see here is now on the y-axis, the angle which is rolled out. That's the reason why it doesn't switch over to 0 at 360 degrees. And at the bottom, you see the frame rate. And by that, even if we have a small outlier, we can say, okay, we go with our fitted line. With that, we taught the computer the way to go for the perception of the temporal component. The other one is that we know if the puddle is just starting to submerge, it cannot be above the water directly afterwards. at least not for the cases we want to analyze. And that's where we implemented some filtering and temporal components to detect single errors. What you can see here is now that we have sigmoid function, or better called the double sigmoid function, where we say if you are in one state, then the probability must be one that you stay there. And if you have changed to another state, then the probability for that one is also one for quite a while, and you cannot go back. You only have the chance to go from one state to the next and not back, and also not jumping over one state. So if you're above the water, then the next state has to be that it is penetrating the water and not directly jumping to the state of being below the waterline. What also helped is that we got new training data. The Olympiastützpunkt, the performance center, went for a HD camera. We had multiple images now instead of single images, which also helped again with the temporal component and getting an idea also there. Just rebuilding how does the biomechanics do it when they look at the video. They also have an idea of the image that was there before. They look now at the computer, and also giving that. We improved the models for training, and with that, we reached a 95% accuracy on the training data we fed in. So there again, giving them the paddle state, the neural network, and then in the end, having the detection, also with hands and stuff. And with that, I would like to jump to the conclusion and going a bit forward here. We have now really a successful analysis. If we look now here, we have a very robust puddle detection. You can see here the blue angle is following closely to the paddle, getting a robust detection of the hands and the paddle itself. That works really well. We also have now a much smoother detection of the paddle state changes. So above the line, under the penetrating and underwater also works now way more reliable. Where do we have problems? Problems is when we have multiple athletes. When there is more than one paddle in the image, then we're still quite off, because the computer was never trained for handling and also differentiating between several athletes in one image. So that's the point where we say, no, that doesn't work. So if we go for the analysis, the athlete has to be the only one in the video. And having now a fully annotated video is what you see here. On the very top left, we have the angle, and then we have the frame below it, both in red. We have in green the waterline, and now here a smooth continuous analysis. How good did we do now? Well, we have a very robust paddle detection. We have a very robust waterline detection, and the paddle state detection went from directly correct in 70% of the cases. We covered roughly 20% are off by 1 or 2 frames, where also the performance center said, well, that's close enough to what a human does. Sometimes we're also not very sure if we're at image A or A+1, and 10% of the analysis is off by more than one, where the biomechanics afterwards has to manually intervene. And how did we improve the overall performance and time consumption for an analysis? Well, if you put in a whole or a bunch of athletes of videos, they can run overnight. So that's where the computer does the work after the analysis, and that takes quite a while. So we are here at a half an hour to 45 minutes for one video to analyze. That's good enough. I mean, if the computer does that overnight, it doesn't need to be supervised by a human. And in the end, you still need to screen the results and sometimes correct them a bit. So there is still some manual work, but overall, we achieved a 90% reduction in manual labor in the Canoe analysis. and how does it look like in the end for what we really hand out. Yeah, we hand over a report where we give here the 4 paddle states and say, it's a bit harder to watch, where we say, okay, here we have found the paddle touching the water. The athlete is at, yeah, let's see, here it hit quite well. So we are here at 70 degrees. We have a correction of 0.1 degrees and say, hey, athlete, that worked. Here we say, no, that should have been a bit more forward. Here it's a correction of 20 degrees. Here it's a correction of 8 degrees. Here it's a correction of minus 12 degrees. And also giving the coach directly in red the line where the biomechanics textbook says that should have been the waterline. We can do that for multiple images. That's also an improvement. Before only one set of paddle state changes was analyzed, we now can give from the whole video the analysis and say, hey, that's multiple paddle state changes to see, was it consistent or was it just a one-off? And yeah, to conclude it, we are now reliable and continuously able to get a video, analyze it. We have 70% of the pedal stages found directly correctly. We can compute the angular velocity without any trackers. That's also quite a nice feature. We export that as a CSV file, so that in the end you can also do, or the performance center can do the analysis by its own, saying we have all the frames, we have the angles, and from that getting the angle velocity at all points, making other analysis about acceleration of the paddle and further component analysis where I'm out of range because it's not my sport. I do not have any significant knowledge on that, and also pushing towards a fully annotated video that I've already shown you, that also then the coach has an idea, okay, at which angle are you at which position when you're rowing. Outlook, what can we imagine if we now have this cool feature and say, hey, what can we do next? What could we imagine? I mean, what we built so far, I would say is quite cool. We could think about real-time feedback, that you have the video streamed directly to the cloud and then analyzed and giving the feedback back directly with enough computational resources. That should be surely possible. And other stuff, I mean, especially for kids, that could be cool to have kind of a gamification, who did best in that test, and having in the end kind of a leaderboard to bring in some play with how to improve my technique, and at the same time having some competition and outlook there to see, okay, how did the others do? And yes, with that, I would like to conclude my talk, and if there are any questions, I'm more than happy to answer. Thank you very much.
All right, Mark. Thank you. Thank you for allowing us a look under the hood of what you have been working on. Thank you very much. And before I open it up to the floor to submit any questions through the chat or Q&A, just one question: how many medals did that yield in Paris?
The Canoe athletes did quite well. I have to admit, I do not know how many medals exactly came out of that, but I mean, Heidelberg is one of the canoe training point in Germany. So, and we are quite successful with paddling. So yes, I would say it definitely contributed there.
All right, that's always a good marker to link it to the ultimate success there. All right.
Yes.
As I said, if there are any questions, please feel free to put your questions into the chat. I'll read them out. But Mark, you talked about improving camera technology and using high definition video. Are these specialized cameras? Because we have in our network companies that nowadays record the videos on pretty advanced smartphones. So can you give us a little bit of an idea of the hardware that you used, and whether you think that in the future something like that could be done on your mobile device?
The hardware here was a usually handheld HD camera with 60 frames per second.
Oh,
Um,
okay.
they they used that. I mean, you're on a boat, and if you drop the camera, that's quite expensive. So they went
Mm,
just for a regular HD camera where you have a SD card in a flash memory that you can then stick to the computer. They do not want to have that on the smartphone of the individual biomechanics. That's the reason why they go for that camera. Yes, in general, I mean, nowadays the smartphone cameras becoming better and better. So I would
mm,
say that's definitely possible also on a smartphone camera to record that. The amount of analysis steps at the moment, especially with the pre-trained neural net to detect the pedal changes, that will be hard to run that on a smartphone, on a mobile device directly.
okay.
Because for that you have to host that network that takes a quite a chunk of graphic card memory. But the post detection on probably also some of the feature tracking and seeing the Canoe, that should be doable right now on smartphones. Let's see how quickly they evolve that they can directly run the whole analysis. So far, even for a computer, it takes a proper graphic card to run that
Okay.
analysis smoothly.
Mm, mm, okay. Um, it seems like we have a bit of a techie audience also, and because Andrew posted a question into the Q&A. Any thoughts, Mark, on methods to adjust the parallax error for angle measurements if the video is not always directly perpendicular?
We have thought about that. So far, we assume that the video is taken perpendicularly. What you could do is that you say, okay, I assume that the canoe has a length,
Mm,
and as soon as we are not fully perpendicular, then you say, okay, the canoe length somewhat changed, and with that you could correct for that. That's the way I can assume that you have a perception of how to see if we are not at the perpendicular angle, as you do when you're a human, that you say, okay, the canoe seems to be a bit short on that video. Probably I'm from an angle. I
mm,
also see the athlete from an angle. There would be several ways to take
correct
that
for.
into account and correct for that.
Mm,
So far, we said, okay, we assume that we're filming directly from the side, as the performance center also did before. They also assumed that they're on a perpendicular angle there. So we did not dig deeper into that. But yeah, that would be the ideas I just have right now to say, okay, how correct for that.
yeah, yeah, good. Thank you. I did notice that on some of the images, there was actually a fairly distinct reflection in the water.
Yeah.
How does your image recognition algorithm deal with that?
Um, the waterline is sometimes a bit affected, but the angle change is not that much. We are quite happy with that, and the rest we are quite happy with the foreground-background separation, because that seems to be trained already on also images where you have some mirroring effects, and
Okay.
it's not disturbed by that. It says no, the canoe is the upper part, not the lower part.
Yeah. Okay. Okay. Good. We have a question from Sean, and that is, did you account for pedal length and blade shape or size?
Um, no, we didn't, because we never took the blade shape and into account, except for when we are touching the water. Because with the pedal length, what we do is that we find the hand, find the
Mm,
fingers, and from that we know the pedal is usually quite firmly connected to the hands, at
yeah.
least when the athlete is paddling, and for that, we did not need to care about directly about the paddle length, because also the angle doesn't change if the paddle is longer, because then it's just more submerged. But the hands and the straight line is that what is determining the angle of the paddle towards the waterline. Where we went for the bit, of course, for the paddle shape is when we trained our neural net to detect if if we are or in which of the four pedal states we're in. So if we're touching the water, if it's submerged, if it's emerging from the water. There we fed in many different videos and also pedals. For that we had, of course, several pedal shapes, but all within that Canoe sport. So going for other Canoe sports, there I don't know how our detection would work. I would be curious to try it out actually.
Mm, mm. Okay, good. Because you do the object to background separation, I assume that except there's other boats in the background, obviously what you showed us, but whatever architecture you have in the background and things like that, that really doesn't affect, like if there's on the other side of that water way that you're pedaling, that does not affect the quality of your assessment, right?
No, because we have the foreground background separation. With that, we're quite happy. And as long as there are not other people in, I mean, that's where we detect where the paddle, or that's where we get the information about the paddle from. And as soon as there are other people in that image, then our post detection becomes confused and sees other people, which is his job at that point. And yeah, then the whole stuff becomes messy, but other architecture is not a problem.
Yeah. Good. There was a question regarding making the recording available of this session, and just for everybody's benefit, we will make the recording of today's webinar available via our website. So give us a day or so, and the link should be then on our event side. Yeah. All right, we have another question from Sean. What did the coaches and athletes do to improve with the information?
That's a good question. There I have to admit that the techie parts, and when we hand over the analysis and say we got the task to find the pedal angle and the pedal state changes and hand out the analysis, there I have to admit I studied the wrong field to directly say what they do to improve it. I would say they take that information, say improve on the paddling technique, and then give it later a rerun. But this is just educated guessing there, I have to admit, and would like to forward you to a coach which has more knowledge.
Okay, so you then didn't interact with the sports scientists and you just provided that information.
Yes. Yes.
Okay. Sean also had a follow-on question. Did you also measure force production?
No, we didn't measure any force production. What we did is just the paddle angle over with the individual frames. With that, you can go to paddle speed and paddle velocity, but we do not have any force tracking on the paddle. We also do not have any markers, so it's really just the pure paddle, the pure carbon paddle, which is the athlete using, which is then used in the analysis, but there are no additional markers or sensors.
Yeah, okay. We do have a company here in Australia called 776BC, and in particular in rowing, they actually have clothing that have quite visible markers on the clothing. Do you think that could be helpful in your model, or does your model not need that because you're basically only using the position of the hands and the fingers to determine the pedal?
It was actually the task to make that analysis possible without any markers, because they said, well, if the human looks at it, we do not need any markers because the human can recognize where the paddle is. And then was the task, please do it exactly the same way. We would like to have an analysis which runs without any markers.
Yeah, okay, good. There's a question from David. Is the model trained such that it can be used with multiple athletes in one boat? K2, K4.
I would say no, because so far we just went for one pulse detection of
Mm.
one person with one pedal, but the applied principles, I mean, that should be extendable to multiple persons.
Okay, good. And another question from Andrew, and he's following up on the multiple subject issue. Are there options to incorporate crowd detection pose estimation routines to create the multiple bounding boxes?
Not yet so far,
Mm.
because I mean the budget of the performance center was not unlimited. To be fair, it was limited. I mean, in Germany, soccer is very, very famous, and if you go away from these very popular sports that you see in TV, then the funding becomes a bit less. And also here, so this project also had some budget concerns. There are many things possible. The AI technology is improving quickly, but here we said, okay, no, we keep it with the most simple version that actually does the task that we were given and not
Mm.
extending it much more. But yes, in principle, we could think about applying various technologies also for crowd detection and multiple
Yeah.
person detections.
Okay. Um, Aishi has a question. What do you see as the long-term potential for AI and computer vision in revolutionizing athlete training across different sports?
Very significant. I mean, the the amount of data that is produced is rising quickly.
Mhm.
You have more and more data available. You have better technologies, AI technologies, computer vision available. OpenPose, YOLOV also developing further. So with that, you get more data. Uh, at least for my taste, at the beginning, you will have a lot of data with not that much knowledge on how to do it and how to analyze it or what to do with it. But then you gain more data, and then the data scientists come in and say, okay, now we have many athletes to compare. We also can feed other information in that this athlete was particularly successful, this wasn't. Do we see any outliers in the trainings data of that athlete over the years? Because, I mean, if you look at an athlete only once, that is a very, very small sample. And yes, I would say we are now in the phase of the capability of gathering more data. And when we have more and more data, then in the end, we will be able to also deduce further analysis from that. So I would say, yeah, there's a lot of potential in that area.
Mm, mm. And there's also a follow-on question. In terms of, do you see with what you have done now to expand this technology beyond the sport that you have been looking at the moment?
Sure. I mean, we also would like to interested in cooperation and partnership with others that want to extend it. I mean, we are a consultancy. We have the cooperation with the Olympiastützpunkt, with our performance center here in Heidelberg. And they said, we have that interesting case. And we said, yeah, we agree, that's interesting. We would like to tackle that. And if
Hmm.
somebody else approaches us and says, hey, we would like to get your expertise on analyzing this part, we are happy to talk about that and see if we
Mm.
can cooperate and tackle that problem.
Yeah, yeah. I mean, we had the translation, one of the startups in our network called they were originally called Rowalytics because they looked at analyzing rowing activity,
Mhm.
but where they actually commercialized that was actually in thoroughbred training because they attached their and that was sensor based, yeah. So they attached their sensors to the horses and translated from there. It sounds crazy, but it did work for them.
Yeah, and I would say the concepts we applied here to um, find the pose, find making use of tracking several body parts to then say, okay, we have the angle of any tooling that the athlete has in his or her hand. that is also transferable to many other sports applications.
Mm, mm. Yep. Yep. Which also highlights, I mean, if you show, you showed obviously multiple athletes and multiple boats in the same frame create a problem. And that's, I think, while looking at team sports, why it may be a bit more of a challenge to then actually isolate, like even whose leg is in the frame at that point in time. Yeah, good, good. I'm just looking around if there's any last minute questions for Mark. Doesn't seem to be the case. So, Mark, thank you very much for joining us, which obviously is a very early morning for you. Thank you again for allowing us a peek under the hood of your work and what you're doing. Thank you so much, and I hope you have a great day. And for everybody on this call, thank you very much. Thank you very much for joining us, and we appreciate everybody's time. And like I said, this recording will be made available on the ASTN website within the next coming days. So please visit us at www.astn.com.au. Mark, thank you very much. All the best.
Thank you. It was a pleasure to be here. Bye-bye.
Bye.